Welcome to the Data Science Institute's virtual seminar series. My name is Dr. Sarah Mackey from Lawrence Livermore National Laboratory. Here at Lawrence Livermore, data science has become an essential discipline in many of our key program areas. LLNL is home to many challenging datasets, as well as home to some of the world's most advanced supercomputers. Our data science staff work in a variety of areas, including machine learning, artificial intelligence, big data analytics, statistical inference, predictive modeling, and uncertainty quantification. The Data Science Institute acts as a central hub for our lab's data science activities. We host events like this seminar series in order to introduce new ideas and potential collaborations to our laboratory staff. We invite speakers from outside the laboratory, from the Bay Area and beyond, to share their innovative approaches with our data science community. We're pleased now to include a wider audience in our seminar series through these recordings. You can read about past speakers at our website at data-science.llnl.gov, or you can email us at datascience@llnl.gov. Thank you and enjoy the seminar series. So with all that out of the way, we're now ready to introduce our speaker, Katiana Kontalati. She received her PhD from Johns Hopkins in 2023 in the Department of Civil and Systems Engineering. Her doctoral research revolves around physics-informed machine learning with a focus on high-dimensional surrogate modeling for uncertainty quantification in physics-based and engineering problems involving nonlinear PDEs under uncertainty. She's a contributor to the development of the open source Python software UQPy for modeling uncertainty in physical and mathematical systems. Her work has been published in Nature Machine Intelligence, and she's received multiple awards and recognition, including the Joseph Myeroff Fellowship from Johns Hopkins, the Applied Machine Learning Research Fellowship from Los Alamos National Lab, and many more. She also was selected to participate in the Rising Stars in Computational and Data Sciences workshop. And then finally, I'd just like to congratulate Katiana on her new data science position at Bayer R&D, where she will be applying machine learning to design high-performing crops. So Katiana, when you're ready, go ahead and take it away.
Great. Thank you, Sarah, for this nice introduction and, of course, for the invitation. It is really great to be with all of you here today, presenting some of the work that I did during my time as a graduate student at Johns Hopkins. And it's always great interacting with the people and attending the events organized by the people who work at the national labs. As mentioned in the introduction, I have personally spent the summer doing research at Los Alamos National Lab, which was one of the greatest experiences I've had as a graduate student. And it must be a really exciting time to work at Lawrence Livermore right now with the nuclear fusion breakthrough, which can really change the energy landscape globally. And I know that many of you who attend the seminar have an interest on uncertainty quantification, scientific machine learning, and high-dimensional surrogate modeling specifically. So I really hope you can learn something from this presentation. And hopefully we can have some interesting discussions afterwards. So with that, I would like to start with an outline of the presentation. I will first begin with some background on the motivation behind this work. Then I'm going to focus on the contributions of my thesis, which is based on the idea of learning in latent spaces for problems from 3 different categories, including inverse problems, forward problems, and transfer learning. And finally, we'll conclude with a brief discussion and some key takeaways in future research areas. All right, so starting with introduction, continuous phenomena that appear in a broad spectrum of fields from physics, chemistry, and biology can be quantitatively described by ODEs and PDEs. And over the past few decades, there has been a tremendous progress in understanding complex processes that take place on multiple spatial and temporal scales. Now, although in physics systems are often treated as deterministic, in reality, they are associated with a number of uncertainties and errors that can appear in physical experiments, mathematical models, and numerical simulations. And so we typically classify the sources of uncertainty based on the degree to which these are inherent to the application, which are the aleatoric uncertainties, or they reflect some sort of lack of knowledge, which are the epistemic uncertainties. And of course, in the field of uncertainty quantification, we are interested in characterizing, propagating, and reducing the uncertainties that are associated with these systems, which is really important in engineering as it allows us to perform risk modeling, reliability analysis, and design optimization. And typically, UQ is performed via repeated evaluations of an expensive numerical model. also known as Monte Carlo simulations. But because this can be really expensive, we tend to rely to scientific machine learning and surrogate modeling. So what is scientific machine learning? So scientific machine learning draws tools from both machine learning and scientific computing to construct predictive physics-based models that ideally share certain characteristics, such as that they are scalable, domain-aware, robust, reliable, and interpretable. And the schematic here shows really nicely the three possible regimes of a level of understanding of the problem's physics, as well as the available data based on which a method can be chosen for a particular application. Now, one of the main challenges in this area is that in physics and engineering, we often consider very high-fidelity simulations that provide a very detailed representation of the system at hand. And so these simulations may involve complex physics, fine discretizations, and uncertainties that can lead to very high-dimensional quantities of interest. So as a result, the datasets that are constructed are both sparse and high-dimensional, which can really harm the quality of the predictive model and significantly slow down or even completely prohibit its training. Likely data that are generated by these physics-based simulations possess a lower dimensional structure that can be exploited to enhance surrogate modeling. And the structure can be essentially discovered by dimension reduction methods. So very briefly, dimension reduction aims to reduce the number of features or dimensions in a data set while retaining as much information as possible. So let's consider that we have a data set of n points that live on this d-dimensional space. We can define a linear or nonlinear mapping phi that maps points x to points z, and the resulting dimensionality d is much less than the original one. So we might be able to also optimize this mapping by minimizing some sort of error measure, which can represent the reconstruction loss computed by the mean square error, for example. And we might also be able to compute an inverse mapping, phi inverse, to map point z back to points x. So from the latent space back to the original space. However, this inverse mapping may not always exist. And in fact, we categorize methods based on this property. So a very famous method that does have an inverse mapping is the autoencoder, which essentially learns to copy the input to the output by minimizing a reconstruction loss. Whereas a method that doesn't have an inverse mapping is diffusion maps, which essentially seeks a lower dimensional representation without being concerned about the loss of information during reconstruction. So dimension reduction has been used quite a lot over the past few years to tackle some of the problems that arise when dealing with high-dimensional data. And here I provide a very brief timeline of methods, more recent works that have used dimension reduction to enhance surrogate modeling and UQ. Despite this work, there are certain challenges that still need to be addressed. So first, some of the more traditional and inexpensive approaches in the literature, such as Gaussian processes, polynomial chaos expansions, cannot naturally handle high-dimensional data. So even though these methods are considered inexpensive, when considering high-dimensional data, performing UQ both forward and inverse can be prohibitively expensive, which really limits their practicability to real-world applications. Second, when considering high-dimensional PDEs that describe complex phenomena such as convection-dominated flows, even some of the state-of-the-art approaches in the literature may result in low predictive accuracy or even fail to converge because of the significant cost of training. However, it seems that there is a tremendous potential in the exploitation of dimension reduction methods to both enable the training and enhance the quality of these models that so far has not been adequately explored. And third, for real-world applications, PDEs are often required to be solved on multiple domains. And as of now, the standard approach is learning in isolation, which requires the collection of datasets and training of models separately. However, we know that models that are trained on different but similar domains are correlated domains possess a common intrinsic structure that can be potentially exploited to enhance multi-domain learning and generalizability, even when scarce data is available. So in view of these challenges and gaps in the literature, the objective of this project is to explore the idea of leveraging both the intrinsic data structure and the intrinsic model structure to enhance predictive modeling UQ for these high-dimensional PD applications. All right, and so for that, I would like to quickly move on to the first part of the presentation, which focuses on inverse problems. And specifically, this project focuses on the atomistic informed PD calibration via a method that we call Grassmannian EGO. And this is in collaboration with Darius Alex Williams and Michael Falk from Hopkins, Chris Rycroft and Nicholas Boffey from Harvard at that time, and of course, my advisor, Michael Shields at Johns Hopkins. So just a brief introduction. As I'm sure you all know, multi-scale modeling allows us to explore the behavior of a system at one level by using information from different levels. So in coarse graining specifically, we're interested in reducing the number of degrees of freedom in a system. So we typically follow this bottom-up scale bridging approach and construct a continuum level description that uses larger time steps and spatial domains in the simulation. So let's consider that we have simulations at 2 fidelity levels. We have an atomistic simulation, like a molecular dynamics simulation. And we also have an upper scale PDE model that describes the evolution of a system in a coarser scale. Now the question is, can we construct a PDE model to generate a response that is consistent with the atomistic simulation? And that is the objective of this project. And first, I'd like to show you an overview of the proposed methodology and then focus on its distinct components. So let's assume that we have our lower scale discrete atomistic model L. The first step in this process is to perform some sort of coarse grain protocol and reduce the number of degrees of freedom and generate the coarse grained fields. This could be the potential energy, the defect density, and these will be our reference fields. And we consider that these are high. Now, these are the ones that we want to be able to match by optimizing an upper scale PDE model represented by a set of PDEs. Let's call this model M. And so this model is associated with a number of uncertain parameters. So we can have different types of parameters. Here we have 2 categories, some parameters that are part of the model, and then some transformation. As I'm going to show you, we use those to essentially generate the input fields that we use to initialize the model by performing a transformation from the coarse grain features of the atomistic simulation to the PDE. And so let's say that we generate a number of realizations of these random parameters, and we run the forward model. We generate a number of continuum fields. And so we want to be able to compute the difference, the discrepancy between all of those fields from the reference atomistic. So what we do is that we project those fields onto a manifold, and here we use the Grassmann manifold, and then we measure the distance between all point pairs. Once we have done that, then we model the distance using a surrogate modeling technique. And then we use surrogate-based optimization to essentially select the optimal set of parameters that yield to the smallest possible distance on the manifold. All right. So was there a question? No. Okay. So before I show you the distinct components of this methodology, I just wanted to mention that we're going to apply this for a bulk metallic glass system. And so bulk metallic glasses are a type of an amorphous solid that are formed when liquid metal is rapidly cooled, so it bypasses crystallization and it undergoes a glass transition. So metallic glasses possess very favorable properties such as high yield strength and fracture toughness. And so here we're going to use the proposed methodology to inform a continuum model that describes plastic deformation in these metallic glasses for a specific metallic glass alloy. All right, so the first step in this methodology is to generate our atomistic simulation data. So for that, we perform a molecular dynamic simulation of an approximately 300,000 atoms of a 50% copper, 50% zirconium alloy. We consider this a 3-dimensional prism with a thin third dimension. And we also consider fully periodic boundary conditions, allowing the system to be treated effectively as 2D. Then we apply shear, simple shear to the quenched glass at a constant volume and temperature until we reach a maximum shear strain of 50% and until we see the formation of the shear band. So this is how these metallic glasses fail, by forming these shear bands. So what we do here is that we perform a coarse grain protocol, reduce the number of degrees of freedom, and here what we compute is the coarse grain atomic energy and atomic strain. And the 2 quantities of interest that we consider in our framework is the stress strain curve and then the shear strain fields. All right, so for our upper scale model, we consider a PDE that is based on the shear transformation zone theory of plasticity. It describes the evolution of an effective temperature field represented by the Greek letter chi. And so this model is associated with 4 calibration parameters. So we have these uncertain parameters that we want to optimize and to which we assign these uniform distributions. And so the bounds in the distributions are set based on some domain knowledge. And so to numerically solve this PDE, we use an implementation that exploits an analogy from incompressible fluid dynamics. So this has been developed by our collaborator, Chris Rycroft. And so in order to initialize the PDE, what we do is that we perform an affine transformation from the coarse grain potential energy to the effective temperature. And we actually learned this transformation as it involves 2 out of the 4 calibration parameters. So if we initialize the initial conditions and we solve the PDE, you can see here how the system evolves and how the shear band forms in this metallic glass alloy. So in order to optimize the continuum model parameters based on the results from the MD simulation, our objective is to minimize a specified distance metric. Okay, so here the goal is to match both the shear strain fields and the stress strain curve between the molecular dynamics and the optimized continuum. And so for that, we have devised the combined distance metric that consists of 2 terms. So delta tau here, which corresponds to the stress strain curve, is computed as the average of the absolute differences between reference and predicted stress values at all simulation time steps. Delta gamma, which corresponds to the shear strain fields, is computed as the average of the distance metric that essentially computes the distance between all the high-dimensional shear strain fields on a manifold known as the Grassmann manifold. So quick tangent here, and very briefly, the Grassmann manifold is defined as a set of all p-dimensional subspaces embedded in Rn. It is an orthonormal matrix manifold, meaning that each point on it is represented by an orthonormal matrix. So if we want to project the point onto the Grassmannian, we just need to perform an SVD, a thin SVD. And we know that the left and right matrices of the SVD are 2 orthonormal matrices, and so these live on 2 Grassmannians. And so here's a very simple example where we have this data set of these 3-dimensional points, and we want to project it. And so these points are constrained by this relation. So we want to project it onto the Grassmannian 1,3, which is represented by the unit sphere. And by performing that projection, we can see that we can both reduce the dimensionality of the data as well as reveal its intrinsic structure. All right, so what we do here in order to measure the distance between the reference atomistic and the continuum is that we project all of those samples onto the Grassmann manifold, and then we measure the distance between all point pairs. So by performing this dimension reduction, we're able to both reduce the computational cost, and as we remove some of the redundant and noisy features in the data set, so we're able to improve the quality of the data. But most importantly, the reason why we want to perform this projection is that it really allows us to identify the structural differences between our data points. So it allows us to create a much more meaningful distance metric. And so once we have computed all of those, the distance between all point pairs, we can a data set of points x and y. So x represent the calibration parameters, y are the manifold distances. And so what we can do is that we can feed that to a supervised learning algorithm. Here we're going to train a Gaussian process surrogate, which of course can provide this prediction with uncertainty measures. And so very briefly, for those of you who are not familiar, in Gaussian process, we assume a Gaussian prior, so zero mean Gaussian process where the covariance function is computed by using a Gaussian kernel. So we can define the joint Gaussian prior distribution, where x here represents a set of trained data, x represents a set of test data. So what we do is that we would condition the observations, compute the joint posterior to make the predictions on this unseen data set. And so once we have constructed the surrogate, then what we want to do is we want to select the optimal set of parameters that yield to the smallest possible distance. So for that, we employ the efficient global optimization algorithm, or EGO. So the EGO algorithm essentially leverages the GP surrogate and its Gaussian uncertainty to iteratively resolve the objective functions in areas where minima are likely. So after we train a surrogate with an initial set of points, a learning function known as the expected improvement function is used to essentially allow us to select the location of each new point. So the expected improvement consists of 2 terms. And so its maximization consists of balancing both exploitation, so we want large improvement, as well as exploration. So we want to explore the entire parametric space. And so once we perform the EGO algorithm, we select a new set of parameters of the model parameters. And so we run the actual continuum model for these parameters. We compute the combined distance as we discussed before, the distance of the manifold, and then we append this new sample to the training data set. Then we reconstruct the Gaussian process surrogate and we perform EGO again to select a new point. So we repeat this process until we end up with a distance that is less than the threshold. All right, and that sort of concludes the proposed methodology. So let me just quickly move on to some results. And so our first objective here is to validate the methodology. So for that, what we do is that we select as reference the full field solution of a forward model evaluation having fixed target parameters. So we want to be able to see if our methodology, Grassmannian EGO, is able to converge to those parameters. So what we do is that we generate 400 training data, and we perform 800 more EGO iterations such that each subsequent sample is selected as the one that maximizes the expected improvement. The process is repeated 9 times to ensure reproducibility of results. These are the different colors that you see here in these plots. And so these plots basically represent the convergence of the 4 calibration parameters, which show both the reduction in the uncertainty as well as the consistent convergence of the parameters to the fixed target values, which is represented by this black dashed line. All right, another thing we can see is to compare the shear strain field and the effective temperature field between the reference and the optimized continuum. So here, if I let those movies run, you will see the evolution of the system. And you'll see that the continuum, the optimized continuum, is able to predict the formation of the shear band, just like we see in the reference one. We can see both good agreement between the shear strain fields and the effective temperature fields. And we can also match almost perfectly the stress strain curve between reference and continuum. So now that we have validated our methodology, we will apply it for the actual copper zirconium metallic glass system. And so here are some results. So here you might notice that we perform many more EGO iterations, 8,000 approximately, because the problem was more challenging. Now we don't have a reference to compare the fixed parameters as we had in the previous case, but we can still see that the 4 calibration parameters, we can see the reduction in the values as well as the convergence of all of these parameters. And so we can again compare the movies between the shear strain field and effective temperature field between the reference MD and the continuum. And again, if I let those movies run, you will see that the optimized continuum predicts the formation of the shear band. Clearly, the model favors the formation of thinner shear bands with more concentrated shear localization. What's interesting is that even though we do not aim to explicitly match the effective temperature fields, we see pretty good agreement at the different stages of the deformation between those fields. Another thing we can see is that we match pretty well the stress strain curve, both in the linear elastic regime and stress overshoot, but also the steady state. So clearly, Grassmannian EGO is able to converge to the best possible fit. So if we wanted to produce an even better match, we would have to go back and improve some of the more fundamental components in this methodology, such as the coarse graining methodology or the means of transformation that we use in order to initialize the initial conditions to run the PDE model. And so we anticipate that this approach can also find use in other types of material systems, so crystalline, non-crystalline, polymer, soft materials, etc. And so with that, I would like to quickly move on to the second part of the presentation, which focuses on forward problems. And specifically here, I'm going to talk about the idea of constructing deep operator networks in latent spaces for high-dimensional and time-dependent PDEs. This project is in collaboration with Somdata Goswami and George Kaniadakis from Brown University. And just a brief introduction. So operator regression allows us to construct discretization invariant surrogates that allows us to approximate mappings between infinite dimensional functional spaces. And so the problem that we have here is a nonlinear operator G, which again maps X to Y, and we want to approximate that through a parametric operator G of theta, where theta is a finite dimensional parameter space. And so this is still trained in a supervised learning manner. So we still need to have a set of labeled data that have been generated on a discretized grid, but that once we have trained them, then we can use it to perform interpolation, extrapolation naturally. And so there are a few neural operators that have been developed over the past 2 or 3 years. Here we're going to consider the Deep Operator Network, or DeepONet, that was developed in the research group of Professor Kaniadakis, and it is based on the generalized universal approximation theorem for operators. So the DeepONet is essentially a composite type of neural network that consists of 2 deep neural nets, a branch net that encodes the input functions and a trunk net that encodes the spatial temporal locations. The output is computed via the dot product of the 2 outputs of the 2 deep neural networks. And so here we're going to train DeepONet using a standard regression laws in a supervised manner by, as I mentioned, generating a set of labeled observations that have been generated on a discretized grid, just like we do with any surrogate modeling technique. All right, so the DeepONet as a neural network-based model can naturally break the curse of dimensionality. However, as we discussed before, the high-dimensional data that are created by fine discretizations and uncertainties can really hinder the optimization of our network and significantly slow down or even prohibit its training. So the idea is how we can use dimension reduction to both enable and enhance the training of DeepONets. And so there are some recent works, and here I provide a small list, that have explored the idea of training DeepONets in conjunction with dimension reduction methods. Despite this work, the question of whether the predictive accuracy and generalizability of DeepONets trained on a latent space is actually improved and how that compares to standard neural operators still remains an open question, and in this work we aim to systematically investigate that. So let's again define the problem here. We have our operator G that we want to approximate that with a parametric mapping J of theta with a set of training data. So what we'll do here first is that we want to leverage a dimension reduction method. And so there are many methods that we can choose. Here we consider the autoencoder, mostly due to their flexibility in the choice of the model architecture, as well as the inherent inverse mapping that they provide. And so I'm sure all of you are familiar with the autoencoder. Essentially learns to copy the input to the output. Here we want to leverage the useful latent representation that is able to generate through this bottleneck architecture. And so once we have trained our autoencoder, we can take the input and output data that we have, we can perform a forward pass of the pre-trained encoder, and then we can train our DeepONet in the latent space. So there are a couple of things that I want to highlight here. So first, the input to the branch net is a set of the reduced inputs that have been generated through the autoencoder, whereas the input to the trunk net is the set of the temporal locations. So you might notice that we don't have the spatial locations here, and this is because these have been convolved through the dimension reduction process, which means that the latent DeepONet can be used for temporal, but not for spatial interpolation or extrapolation. And this is one of the main limitations of this approach. And so what we do here is that we train using a standard regression loss with a set of labeled observations in order to minimize the distance between the reference and the predicted reduced outputs. And so once we have done that, then we can use the model for inference. So what we do is that we generate a new input. We perform a forward pass of the pre-trained encoder to reduce its dimensionality. We perform a second forward pass of the pre-trained DeepONet. And finally, we also use the pre-trained decoder to map that back to the original space. And so we will refer to this entire three-step process as our latent DeepONet. And so the objective of this work is to be able to evaluate the capabilities of L-DeepONet for a set of PDEs of increasing complexity. Then we want to compare its performance with standard DeepONet to see actually whether the accuracy is improved when we train in the latent space, and also perform it with another neural operator, which is quite famous, the Fourier neural operator, or FNO. And as I'm going to show you from the results, by doing so, we're able to improve the predictive accuracy in PDEs of varying degrees of complexity, and also improve the efficiency, the computational efficiency, because we actually train networks that are smaller in size. And so let me show you some applications here. So as I mentioned, we aim to cover a broad range of applications. So we test the performance of L-DeepONet in 3 PDEs of increasing complexity. So the first problem involved the propagation of cracks in brittle materials, where the initial position and length of the crack is considered to be a random input. And the quantity of interest here is the local strain history functional. Next, we have the Rayleigh-Benard convective flow, which is essentially a thin layer of a fluid that is heated from below. And because of this temperature gradient, we have this instability that occurs in this buoyancy-driven fluid flow. And finally, we consider an application from atmospheric physics, where we essentially aim to provide a surrogate to predict the evolution of a jet stream in terms of its velocity field as a result of a small random perturbation that is added to the initial thickness of the fluid. So I'm going to show you the results for the third application, which I think is quite interesting. All right, and so in this visualization, which I hope you can all see, we consider the problem from atmospheric physics. And here you observe a polar jet stream in the Earth's northern hemisphere, which is essentially a belt of westerly winds that evolves in space and time. So this jet is created by the convergence of colder masses descending from the Arctic and hotter masses rising from the tropics. And this visualization uses weather and climate observation to model nearly a month of the jet journey over North America. So being able to accurately predict the evolution of a jet stream is really important in weather forecasting, but also in air travel. So several airlines try to flow with the jet stream to reduce the cost of fuel and flight time. So here we're going to model the jet stream using the spherical shallow water equations, which again use to model the dynamics of large-scale atmospheric flows. The system that we have is a coupled PDE that consists of two quantities of interest, the velocity field that is tangent to the sphere, and a height field, which represents the thickness of the fluid, EH. So what we consider here is a spherical domain, which represents the Earth. And what we consider is an initial basic zonal flow that represents a typical mid-latitude tropospheric jet, and an initial height field to which we add the small Gaussian perturbation to induce the development of barotropic instability. So we can define both the initial condition of the velocity field and the Gaussian perturbation analytically, according to these relations here. And so if we select a set of initial conditions, solve our PDE numerically, you'll see here how the system evolves. And so the two parameters that we consider to be random here, so where the randomness comes in this problem, is from the length scale parameters of these Gaussian perturbation. So we assign these uniform distributions. And so our objective is to be able to approximate the mapping between this initial Gaussian perturbation to the entire time evolution of this velocity field. All right, and so our first step is to generate our data. And so here we have considered a relatively fine mesh of 256 times 256 mesh points, which results in a resolution of approximately 156 kilometers in the longitudinal direction. 72 time steps corresponds to simulation of 15 days. And so I want to show you here in these three movies the evolution of the velocity field by selecting these input parameters of the Gaussian perturbation, three random realizations of those. And what I'd like you to notice is that even with a small difference in the initial perturbation can result in a significant different response in the long term, which really makes the objective of creating an accurate approximator quite challenging. All right, so once we have generated our training data, then we can run and train our L-DeepONet model. We can train it in our standard models, the DeepONet and the FNO. Let me move on to some results here. So what you're seeing here in these volume plots represent the mean square error between the reference and the prediction. And so on the plot on the left, you see the accuracy of the autoencoders with respect to the latent dimensionality. So we use different values here. And as expected, we get slightly better accuracy, smaller errors, we increase the latency, but not major improvement. So you can see that even for a very small latent dimensionality, we get a pretty good reconstruction from the autoencoder. And on the plot on the right, we see the accuracy of the neural operators. So here we have the L-DeepONet, again, with the 4 different latent dimensionalities compared to the standard full DeepONet. So what we observe here is that the latent model outperforms the standard one. In fact, training the standard model was quite challenging as the cluster was typically running out of memory. And we don't even provide results for FNO because for this application, we weren't even able to train FNO because of the significant cost of performing all those FFTs for the high dimensional data. And so what we found is that as we increase the complexity and dimensionality of the PDE, it becomes all the more challenging training those neural operators in their standard version, whereas L-DeepONet can easily handle this high dimensionality by leveraging the autoencoder in this case. And so for a specific realization of the model and the initial condition, I wanted to show here a comparison between the reference evolution and the L-DeepONet prediction, as well as the error. And again, here we have chosen a given random input perturbation for the model. You can see that the L-DeepONet model is able to predict quite nicely the evolution of the system. Of course, the prediction is not perfect, but we are pretty satisfied with that. And that's a full DeepONet model performs compared to the reference, again, for the same input realization. And you can see also here the movie for the error. So what you will observe is that the full model tends from early on in the simulation to sort of smooth out some of the nonlinear features that we see in the reference response and that we wanted to be able to predict them. And so if I show you in this plot, the comparison at 8 specific time steps. So in the first row, we have the reference. In the second, we have the L-DeepONet. third, the full model. Again, you will see that for certain time steps where the reference is quite challenging to capture, L-DeepONet does a pretty good job. It's able to match those maximum minimum values of peaks and valleys that we see in the reference, whereas full DeepONet, again, is not able to capture those, again, also as we go towards the end of the simulation. And we can also see that from the error plots. So here's the error of L-DeepONet as well as the error for the full model. You can see that for the full model, early on in the simulation, the error is quite high, and also as we increase that. And so here I want to mention that we're interested more in the comparison of these models rather than seeing the actual accuracy of the L-DeepONet model, which I think is quite good. And the other thing that we compared is the computational time in terms of the CPU cost. So here are the results for all three applications. Here I show you only the shallow water equation. And so here we compare L-DeepONet with full DeepONet and the FNO 3D. And so by comparing those, you can see that L-DeepONet is significantly faster. Of course, that includes both the cost of training the autoencoder and the DeepONet in the latent space. You can see how significant the cost is for full DeepONet. And for FNO, we do not provide the results because, as I mentioned, we weren't able to train that. So, and again, I wanted to mention that the advantages become more noticeable as we increase the dimensionality and the complexity of the PDE. And you can find more information in this paper that we recently posted on arXiv. All right, so with that, I would like to move on to the third and final part of the presentation, which focuses on transfer learning. And specifically, here we have developed a transfer learning framework for PDEs under conditional shift by using, again, deep operator networks. And again, this is in collaboration with Sombrado Goswami and George Kanetakis from Brown. All right, so the problem that we have here is quite similar. So again, we have a nonlinear operator that we want to approximate with a parametric mapping with a set of training data, but it is slightly different. So what we have here is two domains, a source and a target domain that we want to solve our PDE in. And for the case of the source data domain, we have plenty of available data, where in the case of the target domain, we have very few available data. And so we consider that the inputs in these PDEs are coming from the same distribution. So you can consider initial conditions that are drawn from the same Gaussian random field. But because we change the PDE domain, the geometric domain, for example, the output is going to be slightly different. And so this problem is known as conditional shift. So equal input marginal distributions, different output conditional distributions. So one way to approach this problem is to train two separate surrogates, right? Which is the idea of learning in isolation. And of course, can be really expensive in case where we have multiple domains that we want to solve our PDE in. On top of that, training a surrogate with very few data can lead to overfitting. So what we want to do here is that we want to leverage the idea that networks that are trained on different but somehow correlated domains possess this common intrinsic structure. And so we want to be able to transfer the knowledge that we have gained from the source domain to the target domain. And so as I'm going to show you from the results, this would allow us to mitigate the need for big data and also accelerate learning because the process of fine-tuning models can be really fast. All right, so here's what we propose for transfer learning in DeepONets. And let's again consider our two domains, the source and the target domain. And again, we have plenty of data for the source domain, very few data for the target domain. So the first step in this process is to train our source model. So that would be a standard DeepONet. In this case, we have chosen a DeepONet that has a CNN in the branch net and a fully connected network in the trunk net. So we train it using a standard regression loss in order to obtain the optimal set of parameters, which we denote with theta S star. So once we have done that, then we transfer those parameters to a second network that is identical in architecture. And so what we have done is that we have freezed most of the layers of the network, specifically the convolutional layers in the branch net and all of the layers in the trunk net except the last one. So you can see the red ones are the ones that we leave free to retrain them. And so that is a process of freezing and fine-tuning is quite common in transfer learning. But the main contribution here is in the loss function. So here we have considered a hybrid loss function that consists of two terms. We have the standard regression loss that we usually use to train our DeepONets, but we also add a second term, which is the discrepancy loss known as the COD, which I'm going to explain in the next slide. So while the standard regression loss allow us to match individual samples in our data, the COD allows us to preserve the global properties of the target distribution. All right, and so what is the COD and how do we compute it? So COD stands for Conditional Embedding Operator Discrepancy. It essentially allows us to measure the discrepancy between two conditional distributions. It is inspired by the maximum mean discrepancy, which operates on marginal distributions. And so let's consider that we have two data sets, DP and DQ, with inputs and outputs respectively. To compute the COD, we just need to construct the Hilbert-Smith norm between the two conditional embedding operators, which essentially map inputs to outputs in this reproducing kernel Hilbert space. And so if we expand this norm, you will see that we end up with these two terms, where here phi and psi represent two mappings that are defined implicitly, as I'm going to show you in the next slide. K is a gram matrix that we compute using a kernel. And so if we further expand this norm, you will see that we end up with these three terms. They might look a little bit complicated, but its implementation is actually pretty straightforward because we only need to compute these kernels between different combinations of our data. So why do we want to project our distributions on this reproducing kernel Hilbert space in the first place? And so let's consider that we have X and Y, which are the original random variables in spaces omega X and omega Y. Conditioning directly on X may lead to a complicated problem. So standard approaches such as kernel density estimation can be very challenging for this real-world high-dimensional data. So what we do instead is that we use a so-called kernel trick, which allows us to embed our distributions onto this higher dimensional feature space. And so what we know is that we can define these mappings implicitly. And so we know that the inner product of these mappings is equal to a kernel. And so we can use different types of kernels, like a polynomial, a Gaussian kernel, to do that based on the kind of data that we have. In this Hilbert space, we can compute certain quantities, such as the mean, self, and cross-covariance operators. And from those, we can very easily compute the conditional embedding operator, which is computed very easily as the product of the cross-covariance times the inverse of the self-covariance. And so that's essentially equivalent to embedding our distribution from the original space, the conditional distribution from the original space to this Hilbert space. And so if we have a specific data set of points X and Y, we can compute the empirical estimator of this conditional embedding operator as such. And if we have two data sets that we want to compute their discrepancy, we essentially have to construct this Hilbert-Smith norm between those two conditional embedding operators, as I showed you in the previous slide. And so this approach has several advantages. So first, it does not require any assumption about the underlying probability distribution. At the same time, it is very versatile. So different kernels can be used, both common and custom, to capture the complex patterns in the data, which can be really useful for a wide range of applications. But of course, we have to be careful about how we choose the kernel in this process and how we also choose the hyperparameters in these kernels. And so going back to the hybrid loss function, here the function consists of these two terms, the standard regression loss and the COD loss. And so for the regression loss, we just need to use the labeled data set for the target data, whereas for the COD loss, we need two data sets. First, we use the labeled target data set, and then we use an unlabeled target data set where the labels are computed through the prediction of the model. So what we do is that we want to minimize the discrepancy between those two distributions to essentially preserve the global properties of the target data, the target distribution. And we're going to achieve this by fine-tuning the model as we described earlier. And so with that, I would like to quickly move on to some applications. And so here we consider, again, three applications. The first is the Darcy flow, where we consider a shift in the geometric domain. So we consider different transfer learning scenarios here, you can see in this table. In the second, we have an elasticity model where we change both the geometric domain as well as we shift some of the model parameters. And in the third application, we consider the Brusselator diffusion reaction system, where we change the model dynamics by shifting some of the model parameters. So let me show you the results first for the Darcy flow. And so here our objective is to map the random input conductivity field to the hydraulic head h of x. So here we consider we generate the inputs from a Gaussian process surrogate, a Gaussian random field. And so the transfer learning scenario we consider is a square that we want to transfer that to a triangle with a vertical notch. And so in these plots here, you see the relative L2 error between reference and prediction with respect to the number of training data. I just want to highlight that the x-axis here is not entirely equispaced. So here we jump from 250 to 2000. And so on the plot on the left, what we see, we compare the accuracy of the transfer learning DeepONet compared to DeepONet with random initialization, so the standard model we would use. So we can see that for very few available data, transfer learning outperforms the standard one as we increase the number of training data, and somewhere between 250 and 2000, that is this crossover where after that we have plenty of available data, so we don't need to do transfer learning. And so on the plot on the right, we compare again the transfer learning with the addition of the COD in the hybrid loss functions and without it in the blue. And we can see that for all test cases, adding the COD really improves the accuracy of the model. And so here I have another transfer learning scenario. So we have this square with a vertical notch. We want to transfer that to a square with 2 horizontal notches. Again, we show the relative L2 error between reference and prediction, and you can see the transfer learning, again, outperforms the standard one with very few data. As we increase data, you can see that the crossover here happens a little bit later, around the case of the 2000, but still for 2000 data, we see comparable performance from the two models. And here are some test cases, some representative results, where here we have the input random conductivity field for the triangle and the square domain. And this is a reference response, the ground truth, and the error of the transfer learning. You can see here from the color bars that the error is quite low. And also we wanted to compare the training cost in terms of CPU time for the Darcy flow and for all transfer learning scenarios. So what we did is that we compared the standard DeepONet with the transfer learning DeepONet for the same number of training data. And of course, we found that transfer learning is much faster. And of course, this is something expected as, again, we trained a network that has very few layers, very fewer parameters that we want to optimize. And of course, we first need to train our source model prior to performing transfer learning. So we have to also include that cost. But what we have found in general is that these results become all the more important as we increase the number of target tasks we want to perform. And finally, I wanted to show one of the limitations of this approach, because I think it's also important to discuss that. So here we wanted to find a case where the source domain and target domain are very different. So we wanted to push the transfer learning approach to its limit to see its limitations. And so this is for the elasticity model specifically, not for the Darcy flow. But what we have done is that we have changed the geometric domain. So we have here this square domain with a square inclusion. And for the target domain, we have this irregular polygon. But we have also changed the model parameters, specifically the Young's modulus and Poisson ratio, quite significantly. And so what we found by doing so is that for one of the two quantities of interest, specifically the vertical displacement in the model, the prediction of the transfer learning model significantly deviated from the standard approach, again, for the same number of training data, which really showed us that when we have significant differences between source and target domains, performing transfer learning may not be the optimal approach. Or we would have to go and perform some other techniques, such as progressive unfreezing. So the way we do the fine-tuning in the model by using the source model that is pre-trained. All right, and so with that, I would like to quickly wrap up and move on to the discussion section. So I wanted to first provide a summary of the contributions that I showed in this presentation. So first, we discussed on how we can parameterize and calibrate PDEs based on results from atomistic simulations and how we can generate responses that are consistent, how we can train surrogate models in latent spaces and leverage these latent representations to enhance predictive accuracy, but also enable training. And so I also show you how we can use transfer learning to solve PDEs on multiple domains. And some of the key takeaways that I'd like to remember from this presentation is that first, by leveraging the latent data structure, we can both improve the quality of the data and enable training of surrogate models in certain cases that we have very high dimensional data, very high dimensional PDEs. We can, of course, remove the redundant features and accelerate learning. And by also leveraging the intrinsic structure of the models, we can enable multi-domain learning and enhance generalizability. So I showed you problems from a wide range of applications that can be useful to practitioners and from industry engineers to meteorologists. So despite the promising results that I show you in this dissertation, there are certain areas that still require further research. So one of the main limitations of this method is the lack of interpretability in the latent space variables. So being able to relate those variables with some physical quantities may allow us to select them in a more clever way and understand them better. So I think that's an interesting future research area. In many of the problems that I show you here, we considered relatively small data sets, but in reality, we might have even fewer data sets, especially when we consider high fidelity data that are expensive to generate. So being able to integrate some of the proposed approaches with active learning and sequential sampling would be another promising future research area. And finally, another limitation that we found is that when we train those models in latent spaces, these models can perform very poorly in certain extrapolation tasks. And in certain cases, you might not even able to perform extrapolations, as I showed in the Latent DeepONet case. And so these limitations can be addressed by imposing certain constraints in the latent space and introduce certain biases, such as learning or inductive biases. And it seems that there is also an enormous potential in this area as well. Right, so with that, here are some references, some papers that have information based on what I showed you in this presentation. Most of these papers, if you don't have access to the journals, are on arXiv, so you can also find them there. And again, I would like to acknowledge first my PhD advisor, Professor Michael Shields, all of my collaborators, and as well as the Department of Energy for providing financial support throughout my PhD. All right, so with that, I'd like to thank you all, and I'd be happy to take any questions.
Thanks, Katiana. That was very, very interesting. Are there any questions for Katiana? You can either type them in the chat or feel free to come off mute and ask. I have a very basic question for you, Katiana. I'll kick us off since people are a bit shy. So DeepONets are a pretty new topic to me, admittedly, and you talked about the branch and trunk parts of your network. Can you unpack that for me a little bit more and maybe give me some intuition why they're so named? The trunk maybe is important, the branch less so. Can you talk about that?
Yeah, definitely. Yeah, the DeepONet, again, as I mentioned, is based on this generalized universal approximation theorem for operators, which essentially extends the original theorem from shallow neural nets to deep neural nets. So it essentially gives you some guarantees that you can get an arbitrary precision, accuracy, based on arbitrary precision. And so the way that this network works is that it consists, again, of these two terms. So you can consider that if you have a PDE, the inputs to the PDE can be some high-dimensional input random fields that we enter in the branch net to generate some embeddings. In this case, we use a CNN. The trunk net now is the interesting part where we input the spatial-temporal location, and that makes it different compared to other surrogate modeling approaches, where we essentially do a simple mapping. We want to approximate a mapping between two finite-dimensional vector spaces, right? So this is how traditional surrogates work. And so when you train a traditional surrogate, you can use certain input that is basically another realization of the input that you use to train the model and predict on the same spatial temporal locations. But here, because we use this trunk net, which again, here you might consider that we have a 2D PDE, a three-dimensional PDE, which has X, Y, and T. So you essentially train the network for these X, Y, T. And once you have trained it based on data that have been generated on a discretized grid, to do inference, you can use any new combination of X, Y, T. So you essentially, it's like learning the actual operator, right? So this is closer to the real and analytic solution, and that's why people prefer neural operators recently compared to the more traditional kind of surrogate models. So I think the magic, quote unquote, happens here in the trunk net. There are other neural operators like the FNO, which I did not discuss here. But the DeepONet has shown it's very promising in a very wide range of applications. I have trained it for very different PD applications, but definitely understand that it can be quite different than the original sort of surrogate models or even the traditional neural networks that we use to perform regression.
Yeah, thanks. That's helpful to unpack that for me. Are there other questions that people have?
I have a question. Your CFD examples or time evolution CFDs examples, how does this change when you're looking for like a static solution or steady state solution for a CFD problem?
Okay, so essentially, and I assume you're talking about the shallow water equations, which I showed specifically this application.
Yeah, that's right. Thank you.
All right. Yeah. So that's a great question, because in this sort of project we focused on time-dependent PDEs because we wanted to have the time component, which makes it a little bit more tricky. And so if you want to be able to approximate these operators where time is evolved, as I mentioned before, you have to add the time component in the TrackNet. But if you have a steady state, that's totally fine. You will just construct your TrackNet using only the spatial locations. And I would assume that this would be, well, it depends on the problem, but if you exclude the time component, you might make it a little bit less complicated, but still CFD, and I'm not an expert on CFD whatsoever, but I've seen for the type of problems that we're interested in, constructing an operator like a DeepONet for a steady state problem is a bit easier compared to adding the time component, and that's why we wanted to explore that in this project. But definitely, yeah, you can just modify the way you form the TrackNet, and of course in the output you wouldn't have these multiple snapshots, right? You would have just one in case you have a steady state problem. I hope that helped.
Yes, great. Thank you.
Thank you.